This is Mr. Bob, and this session today, you're going to actually see two videos spliced together because what happened was I actually recorded the live session, but I didn't start the recording until I was halfway through the live session. So I'm recording this after the fact to just marry it with the second part of the video, which I actually captured live. So you're watching this recorded, so I'm going to flip through the slides fairly quickly. Feel free to pause at any time, and I will encourage you to pause. For example, here at the warm-up, take a few moments here or a few minutes as you see fit to try and answer those three warm-up questions. Okay, so I'm going to assume you've paused and done what you can with the warm-up, so let's talk about this. If you look at it, these are two coherent light sources, or you can think of this also as you're in a bathtub and those two black dots here are basically rocks or pebbles that you drop in the bathtub or in a lake or something. And you're looking at it from above, and the sort of crests you see there, those little dash marks are crests. Now let's remember, along the center line here, the path difference between the waves from this rightmost source and the leftmost source, there's going to be no path difference, meaning that they're going to be totally in sync with each other. So crest is going to be meeting crest along the way and trough meeting trough. And so you're going to get that central maximum. If you remember, kind of looks like this, if you were kind of like putting it on a screen or something. On either side, there's a minimum, and then remember there's another maximum and then another minimum, et cetera, et cetera. Okay, so the question is which reference line or lines represent constructive interference? And where crest is meeting crest, where you're seeing those ripples, that is constructive interference. So A and B are clearly those spots. So that's the answer to part A. The other way of thinking about part A is if you think about the path difference between the waves on the right are traveling versus the waves on the left, it's going to be exactly one wavelength. Because remember, constructive interference, I'm going to label that CI. CI, the criteria we learned last time, that occurs when the path difference is either no path difference or multiple whole wavelengths. 1 lambda, 2 lambda, 3 lambda, 3 whole wavelengths. Whoops. Destructive interference, in contrast, remember we learned last session, occurs where the difference between the path that one set of waves from one source have traveled versus the other is half integer wavelengths, if you want to say that, n plus 1/2 times lambda. So notice destructive interference is going to be those half wavelength multiples. So notice C and D are destructive interference because the path difference is, in C's case, 1.5 wavelength difference between the left and the right. In D's case, 2.5 wavelengths. And part C, identify the path length difference for each letter. I just kind of laid it all out there for you. Notice it's symmetrical from either side. You have the central maximum, and on either side, you're going to have basically destructive interference, which is represented by half wavelength path difference, and then constructive interference represented by whole wavelength path difference, et cetera, et cetera. Awesome. Now, today, I want to talk quickly about the speakers, then I want to get into the basically new material, and then we'll get into the rest of the fun part in terms of the Furious Five and the breakout rooms. So Yuka Sashi talked yesterday, and she was fabulous. Really, I can't say enough good things about the way she shared and what she shared about her experience as being a graduate student working in a research lab as a physics graduate student. I highly, highly encourage you to take 40 minutes, even 30 minutes of your time, because the last 10 minutes, I think, are question and answer, to watch. I will be posting a video replay of her talk online here sometime in the next few days. Today, Ann Bentley is talking in a little bit while here, and hopefully you'll get a chance to listen to her speak. She's going to talk about surface chemistry, and it sounds fascinating. Reminder, tonight, May 14th, Legacy Project Progress Update number 2 is due, and then Thursday the 21st, the third project progress update is due. Remember, the overall goal is for you to be done with this project 2 weeks from today, on Thursday the 28th, no later. I also want to put in a plug for Quantum Spot Academy video that I posted a few days ago to the blog. It is a fabulous explanation of the weirdness of quantum mechanics. And now that you have the background of understanding how sometimes particles behave as waves and waves behave as particles, you have a depth of knowledge that can help you to appreciate this video even more and become even more fascinated by the weirdness and the counterintuitiveness of quantum mechanics. I highly encourage you to take 15 minutes to watch that sometime. Okay, let's get into the new material. The question for today is kind of, let me just start with a scenario. Let's say you're driving at night and you see a light source off to the distance. And the question is it truly one light source or two light sources? And how can you tell? And that's an interesting question. And it's not just like an interesting thing. It's also something that has some very significant applicability to physics that you're going to see here. If you look at this animation of this Jeep, the headlights on this Jeep, if it's far enough away, it's going to look something like that, what you see there. And then over time, as you see what's happening, as it gets closer and closer and closer, you're going to be able to distinguish that there actually are two headlights on the Jeep, a left and a right, as opposed to just it seeming to be all just one light source. So this brings up a question. At what point can any imaging system, our eye is an imaging system, at what point can an imaging system distinguish between two light sources that are pretty close together from each other? So the essential question again, how can we quantify the limits of imaging systems and being able to distinguish between objects? And I just want to emphasize imaging systems are things like telescopes, microscopes, cameras, and your human eye. To do this, I just want to recall one slide from last class. Remember that if you have light or any waves traveling through a small opening, what we call an aperture, then you're going to get a certain sort of diffraction, and you're also going to get spots further down the line where there's constructive interference and then there's destructive interference, right? And you get some sort of interference pattern that looks like what you see there on the right with green. So keep that in mind. Now, with our human eye, and this is just sort of a graphic of it, notice we have two light sources here on the left, and I want to emphasize something right away. This is red and green, but it's not necessarily different wavelengths or different colors of light. I've made them red and green just so that we can distinguish them here on the far right. Imagine they are the same wavelength though, so they're the same color. And again, the only reason I've made them different colors is so that you can see what's happening here with the interference pattern. So if you have, for example, that Jeep on the left coming towards you, your eyeball, it's a small opening, right? So it's going to create an interference pattern. Is going to be created on the rear of your eye near your optical nerve. And those two interference patterns from those two light sources could look something like what you see there. And of course, the dog is barking. So there are different ways, or at different points along the way, the interference pattern is going to look something like any of these scenarios. Notice you're going to go from, these letters will come up here in a second. You're going to go from A and then to B and then to C and then D and E and F. And the question is, at what point can we say that the images are resolved, meaning that we can clearly distinguish one image from the other? Well, this is something that scientists have pondered. And a while back, a gentleman by the name of Lord Rayleigh came up with what he called the Rayleigh criterion, or Rayleigh resolution. And it turns out, by the way, if you were just trying to guess here, A through F, take a second to take a guess. I'm going to tell you the correct answer, at least the Rayleigh criterion, uses C. And notice in C, actually, let's just move to the next slide and I'll show it more clearly there. Okay, so two sources are just resolved using an aperture if the following is true. The first minimum of the diffraction pattern of one of the sources falls on the central maximum of the diffraction pattern of the other source. So notice what we have here is the source, the red source, its maximum coincides with the minimum of the green source, the first minimum of the green source, and vice versa. And that is effectively what we call the Rayleigh criterion. And what it allows us to do is it allows us to tell us the minimum angular separation. Now, there are two equations here that you're looking at, and we're not going to use the middle equation much because we don't really use or work with square apertures most frequently, at least not in the IB curriculum. The circular apertures is what we work with most frequently. Notice it says, and I want to kind of emphasize this a bit, it's saying let's say this is the imaging system here on the right, the eyeball, here's the Jeep on the left, and it says theta equals 1.22 times lambda over b. What is theta? Theta is the minimum angular separation required in order for this imaging system, in this case the eye, to distinguish this as two objects. And that criterion says theta equals 1.22 times lambda, the wavelength of the incoming light, divided by b, and b is the opening, the width of the opening. In this case, it would be the width of your pupil in your eye. I will tell you, some of you are probably saying, whoa, where did this come from? Can we go through a derivation? And honestly, a derivation of this is beyond the scope of this course. But if you are interested in this, I would suggest you look up something called Fraunhofer diffraction. That's a good starting point, and you will certainly get involved in some calculus, and you can follow it through and see where the 1.22 comes up with for circular apertures, okay? It's pretty interesting, but again, not something I'm going to go into here. Okay, so now let's use, in the next slides, we're going to use this circular aperture equation and apply it. So, okay, I'm going to talk through this. I'm sorry. It looks like I kept these notes. So we have a car's headlights that are 0.75 meters apart. Now, what maximum distance can they just be resolved by one human eye? Assume a diameter of 4.0 millimeters for the pupil. So notice what we have here is we have the car and we have the distance there. Ignore the purple and the green for now, okay? And that's 0.75 meters. So the first thing we have to understand is, given that our pupil of our eye is 4.0 millimeters, what is the minimum angular separation that is going to be required for the eye to resolve it? Okay, so you're going to use this equation for circular apertures. Theta equals 1.22 times the wavelength divided by the width of the aperture. So you're going to put in the wavelength of 530 nanometers, 530 times 10 to the -9th meters, and divide it by, divided by the diameter of the pupil, which is 4.0 times 10 to the -3 meters. And we get that the minimum angular separation required is 1.6 times 10 to the -4 meters. Now, if you look down here in green, what I want to point out is theta is also equal to S over D, where S is kind of, you can think of it as the arc length, and D is the distance from the eye to the car. Imagine this being a part of one huge circle, and capital D is actually, you can think of it as the radius of the circle. So we know that an angular definition in radians is equal to the arc length, S, divided by the radius, in this case D. So theta equals S over D, and we can solve for D, capital D. We know theta from the previous part of the minimum angular separation is 1.6 times 10 to the -4 radians. We know the headlights are 0.75 meters apart. And so we get an answer where the furthest away that this human eyeball will be able to differentiate these two headlights as being separate light sources using the Rayleigh criterion is going to be 4.7 times 10 to the 3rd meters. And that is approximately 4.7 kilometers. Okay. All right. I just talked about that. All right. Now, here's the joke. And by the way, with the joke, the new plan was when you hear the punchline, you're going to unmute your microphones for 2 seconds, laugh, and then remute your mics. All right. So, question, how does a rancher keep track of their cattle? Answer, with a calculator. Awesome. Okay. Sample problem 2A. And here I believe we get to the other video. So I'm going to transition. I have a 68-meter diameter radio telescope is receiving radio signals of 2.0 gigahertz from two stars that are 75 light years away and separated by 0.045 light years. Can the telescope resolve the images of the two stars? Meaning, can it really distinguish that it's two distinct stars there as opposed to just one star? This is a really common concern, common issue in astrophysics. Let's figure this out. Let's make sure we understand this. A problem like this is so important to basically draw a picture, because otherwise you can get really confused. So again, what we have here is that telescope on the left. We have the two stars there. We have a separation between the two stars. And we know that it's about 75 light years away. Okay? So we have this light source, or what might seem to be a pair of light sources, coming from 75 light years away. So the solution. To figure this out, first of all, notice I gave you the frequency of the light source. I didn't give you the wavelength. So the first thing you have to do, is you need to use the wave speed equation applied to EM waves to figure out the wavelength of the light. So the wavelength, when you do the calculation, 3 times 10 to the 8th meters per second divided by 2 gigahertz, gigahertz is 10 to the 9th, so it's 2 times 10 to the 9th hertz, gives you a wavelength of about 0.15 meters. Okay, now with that wavelength, we can then move forward and use our Rayleigh criterion. And we're going to use the circular aperture one because that is circular, obviously. And when we do that, applying the wavelength of the radio waves and divide it by the diameter of the telescope, we get an angular resolution of 0.0027 radians. So again, let's make sure we understand this. That means for that telescope to be able to resolve or see two objects, two light sources as being different, they have to be separated angularly by at least 0.0027 radians. If they're separated by more than 0.027 radians, we're good. If it's less than that, then no, that telescope is not going to be able to do it. So now what we just need to do is we just need to figure out what theta is. Okay, and what is theta in this problem? It's just what we were just talking about, right? It's if this is S right here in arc length, and this is D, okay, it's going to be S over D. So it's going to be 0.045 divided by 75, and we get this number. So now when I compare the two numbers, notice that 0.00060 radians is less than 0.0027 radians. So that single radio telescope by itself does not have the sufficient capacity to distinguish those two light sources as being two separate stars. Okay, the angular separation is too small for the telescope to resolve. This is a really common difficulty that astrophysicists have. So what have astrophysicists figured out? They are quite ingenious folks. And let's look at sample problem 2b to see. By the way, some of you might have thought, oh, I got to convert light years to meters, etc. But not necessary, right? Because as long as you have your units, your separation is in light years and your distance in light years, that just cancels out. So don't always convert prematurely. Okay, so what scientists have done is they have basically put together radio telescopes, and they sometimes you'll see them, maybe you've seen them, I used to see them in Annapolis where I went to school. They are grouped, not just one by itself, but it's a series of them. And here you're going to see why that is so helpful, okay? So let's say in this scenario, we put another identical radio telescope that is 350 meters away, and we synchronize it. And this is really important. It has to be synchronized. So it can be used in concert with the first one to create a single telescope having an effective diameter of 350 meters. So notice we've just expanded the opening of the aperture. So now instead of the B being 68 meters, it's 350 meters. Let's ask the same question. Can the pair of telescopes working together resolve the stars? So remember from the earlier problem, we knew that the actual angular separation of those two stars is 0.0060 radians. So now what we need is we need the capacity of these two telescopes working together to be less than that. And if it is, then that means we're good. And so when we make that calculation, again, it's 0.15 meters as before is the wavelength. For the new telescope, what do we have? We have 1.22 times 0.15 divided by 350 meters this time. And notice in this case, what we get is a capacity of the two telescopes together that is much more, what am I trying to say? Smaller. So in other words, 0.00523 radians is an angular resolution that is much smaller than what the actual, a little bit smaller than what is required to distinguish those two stars. And so in effect, we've been able to increase the capacity of scientists to resolve images that are far away from us. Some of you may be aware of this, but if you recall last spring, the first image, so to speak, of a black hole or the kind of the effects of a black hole around it were created by teams of physicists, astrophysicists working across the globe. And what they did is they synchronized basically telescopes all across the globe. Tremendous sort of coordination was required to basically create one massive telescope basically having the diameter of the Earth, so to speak, and then trained on the same spot in the sky for I don't know how long, but it was a long time. It was hours, or it might even be weeks, in order to get enough data to then be able to construct that image. So it's so much data. I think I mentioned this in class before. It's so much data that the most efficient way to transport the data from one spot to another so that they could all analyze it together was to actually take the hard drives out of the computers, get on a plane, and basically physically carry those hard drives to one location. So keep that in mind. Elena Connolly asks, does having two eyes provide a similar effect? Yes, Elena, providing two eyes does have a similar effect. And I believe, although again, I'm not a biologist, so I'm not sure, I believe we even have other senses and others. Our brain is so adept that our pattern recognition over time allows us to become even, it basically pushes it to maybe even beyond what physics might suggest we're able to resolve, right? This whole idea of stereo vision and stuff and this learning capacity of our brain, I think gives us greater capability. That would be an interesting thing to research. Okay, so like I said, radio telescopes are commonly grouped together in what were called radio arrays. Okay, so just one final slide here. If I want to improve resolution, if you look at this equation, what are two ways you can improve the resolution of your imaging system? Well, one way is to increase the diameter of the aperture. And if you remember Dr. Celeste Yates, the astrophysicist, when she talked to us, she talked about the fact that, you know, the larger the diameter of the telescope, obviously, the more powerful it's going to be, not only in the sense of it'll capture more light, but also in the sense that it'll improve the resolution, the ability for you to distinguish between two objects that are close to each other, because you're increasing the B. And if I increase the B, then I make that theta smaller. And that's the goal, to make the theta smaller. The other way, if you look at lambda on top there on the numerator, would be to do what? Decrease the wavelength, okay? And that is actually the basis of something called an electron microscope. So if you think about optical microscopes, like maybe what you use in biology, have a certain resolution, but scientists have realized that if I use an electron microscope, because remember, electrons have a wavelength, remember a de Broglie wavelength? If I use an electron microscope, its wavelength is way, way smaller than anything in the optical range. And so I can get an incredible resolution of or images of objects that I'm shooting the electron microscope, the electrons in the electron microscope at. Okay, so those are two ways to improve the resolution of imaging systems. All right, here we go. If you have questions about what I said, please feel free to write them in the chat box. I'm so excited about this game. This is gonna be a fun game. All right, so this is just gonna last a few minutes, by the way. So if you're not interested in playing this game, I totally get it. Just hang out for a few minutes while we play this game, and then we'll go to the breakout rooms. But I saw this, and I thought it'd be fun to try it out. So bear with me. So your goal is to accumulate the most points, and you're gonna have roughly, I don't know, 4 or 5 rounds, maybe 6 rounds to accumulate the most points. How do you get points? Well, each round, I'm going to basically ask you to show me an object, okay? So, and then the first 2 people to show it to me clearly on the screen are the ones that are gonna get points for that round. So, for example, if I say, show me a pair of sunglasses, and I'm looking on my gallery view at all of you, you have to have your camera on, then the first 2 people that I see that show me sunglasses clearly on their video are the ones that are gonna get the points for that round, okay? So, and then we'll go to the next round. And the way it's called Furious 5 is because also I'm gonna be counting down. So I'm gonna say, show me a pair of sunglasses, 5, 4, 3, 2, 1, right? And so certainly if 2 people show it to me before I get to 1, that's great, they'll get the points. But if no one shows it to me in 5 seconds, then no one gets any points, okay? So keep that in mind. Okay, obviously you have to have your camera on to play. It is entirely your choice if you want to play. If you don't want to play, totally get it, no worries. Just hang out and watch and be a cheerleader for other people. Only positive comments though. Keep your microphone muted, okay? Otherwise, it could just be total bedlam. All right, so let me see what's going on here if I have anything else. Again, we're only going to go for a few minutes on this. So if this isn't your thing, just hang out. Then we'll get into the breakout rooms. Okay, so I already gave you that example. So let me make sure I get to gallery view here and make sure I can see everyone. Hold on. Okay, I'm going to stop presenting because that way I can get more people. Actually, oh. Hold on, I got to go here. Hold on, I can do this. Get out of there. All right, hold on, I got to take this off. Go here. There it is. Stop presenting. Okay, let me get to gallery view here. Wait, why can't I? This is ridiculous. I should be able to see a lot more people. Oh, wait, are there only 6 of you playing? Oh, there we go. Okay, I see more people now. All right, here we go. All right. Okay, so I'm assuming I see Alex, Avery, Ian, Mitchell, Nick, and Noah playing. I don't see anyone else playing. So if you're intending to play, but you haven't turned on your video yet, you've got a few more seconds to turn on your video. Okay. All right. All right. All right. Let's go. Here we go. HL physicists, you have 5 seconds to show me a shoe. 5, 4. Oh, Nick and Alex Gutman. Nick and Alex Gutman each have a point. All right, here we go. Next one. HL physicists, you have 5 seconds to show me a pencil. 5, 4, 3, 2. Avery and Mitchell. All right, here we go. 4-way tie for first place. HL physicists, you have 5 seconds to show me a pillow. 5, 4, 3, 2. Oh, Mitchell and Alex. Mitchell and Alex are in the lead, each with 2. All right, here we go. HL physicists, you have 5 seconds to show me a textbook. 5, 4, 3, 2. All right, I see. All right, I saw Avery and I saw Ian. Ian's on the board. All right, HL physicists, you have 5 seconds to show me a stuffed animal. 5, 4, 3, 2, 1. Nick and Avery at the last second. All right, HL physicists, you have 5 seconds to show me a data booklet. 5, 4, 3. Alex and Mitchell. All right. Oh my gosh, this is amazing. We have a 3-way tie for first. Avery, Alex, and Mitchell all have 3 points. Nick has 2. Ian has 1. All right, we'll go 2 more rounds. Here we go. HL physicists, you have 5 seconds to show me a calculator. 5, 4. Oh, it was Avery and Alex. Wow. Here we go. All right. Last round. HL physicists, you have 5 seconds to show me a ball cap. 5, 4, 3, 2, 1. Wait, I don't see a ball cap. Like a hat. I got Alex and Mitchell. All right. All right. Good job, everyone. That was fun. Okay, so hope everyone had some fun with that. That was cool. Very good job. All right, so breakout room. Let's talk about breakout rooms. So breakout rooms today, it's quite simple. What I'm going to want you to do is the following. Okay, so we already did that. So the goal for breakout rooms today, can you see that? Is that displaying? If you can't see that, tell me. So if you're in the Super Tic-Tac-Toe tournament and you haven't played your opponent, play your opponent. I put you both in the same breakout room. Collaborate with others on a legacy project if you're working in a group and you need that time to collaborate. You can also submit your progress update, right? That's due tonight. So those are all things you can do in your breakout room, okay? And obviously it's up to you as always how long you spend in the breakout room. I will definitely be checking in the breakout room periodically, each of the rooms.